Hello, my name is Benjamin Lin. Today, I will be teaching you a method for balancing redox equations that is much faster than the traditional half reactions method. As you can see on screen, I'm demonstrating this method right now to solve a problem in both acidic and basic conditions. With enough practice, you should be able to get your solve time down to below 1 minute. But don't worry, today I will be going extremely slow while teaching you the examples, and you can follow along with the guided handout in the description. Also in the description is provided free practice problems from past USNCO exams, so I hope this will be helpful to you. Without further ado, let's get started. So first, the first thing we need to do is identify the atoms that are reduced or oxidized. And usually that's going to be the atoms that are not oxygen or hydrogen in the reaction. So in this case, that's going to be the chlorine and sulfur. So here and here. And then we're going to need to figure out their oxidation states. So this overall chlorate ion is -1. And each of these three oxygens contributes -2. So that implies that this chlorine must be +5. This SO2 is neutral overall. Each of these O2s contributes -2. That means the sulfur must be +4 to cancel out with the two minuses and give a neutral species overall. We're going to ignore waters, H pluses, or hydroxides. And then on the other side, we're going to do the same thing. So here, this species overall is 2-, and each of these oxygens contributes -2. That means this sulfur must be +6. And here, this chlorine is obviously -1 because it's by itself and it's an anion. And again, we're going to ignore H2O, H+, or OH-. Then what we're going to do is figure out how much each of the oxidized or reduced atoms change in oxidation state. So this chlorine goes from +5 to -1. That's a change of -6 overall. This sulfur goes from +4 to +6. That's a change of +2 overall. What we need to do is find the least common multiple of the changes here. So we have 6 here, 6 up here, and 2 here. The least common multiple of 6 and 2 is going to be 6. That means we need to multiply each reaction to get to the least common multiple. So 6, we're just going to multiply by 1. It's going to stay the same. And 2, we're going to multiply by 3. What this means is that we're going to write the chlorine reaction multiply 1. So it's just ClO3-. And then the sulfur reaction, we're going to need to multiply by 3. So +3 SO2, and then we're going to ignore water again, and then here 3 SO4 2- because we multiplied by the sulfur by 3, and then plus Cl-. Our next step is balancing charges. We're working in acidic conditions, so our charge balancer is going to be the H+. So let's figure out the charges on both sides. On this side, we have -1 from the chlorate, and that's it. On this side, we have -6 from the sulfates and -1 from the chlorine. Overall, that's -7. So to balance -1 and -7, we're going to need to add 6 H pluses to the right side. So plus 6 H plus. And now we've introduced hydrogens to the right side. That means we're going to need to add hydrogens to the left side to counteract that. And in this case, that means adding 3 H2O. So now we have 6 hydrogens on both sides. We're done. But if you want to be sure and check your answer, which I highly recommend, at least when you're not in a time crunch, it's what we need to do is count the amount of oxygens on both sides. On this side, there's 3 oxygens, plus 3 oxygens from the chlorate, and then plus 6 oxygens from the SO2. On this side, we have 12 oxygens from the SO4 2- and no other oxygens. And we can see that clearly 12 equals 12. So this is actually the correct answer. Let's try one more example in basic conditions before I speed things up and do harder examples. Here, we have the permanganate ion, -1 overall. Each of these oxygens is -2. That means this Mn needs to be +7. This overall is -2, and each of these is -2. So this needs to be +4, this sulfur. And then here, each of these is -2. That means this Mn must be +4 to cancel out with both of those -2s and give a neutral compound. And to leave an overall -2 charge, with 4 oxygens contributing -2, this sulfur needs to be +6. All right, so now, again, we're going to figure out the changes for each of the reduced and oxidized atoms. So Mn goes from +7 to +4. This is a change of -3. SO4 2 minus, here, let me just make some space. Sorry, SO3 2 minus goes from +4 to +6. This is a change of +2. What's the least common multiple of 2 and 3? Well, that's going to be 6. That means we need to multiply the 2 by 3. So we're going to multiply this sulfur reaction by 3. And then the Mn is going to need to be multiplied by 2 to get to 6. So let's write that out. We're multiplying the Mn reaction by 2. So that's 2MnO4 minus plus. And then we're multiplying the sulfur reaction by 3. So that's 3SO3 2 minus. Ignoring water, we have 2MnO2 and then plus 3SO4 2 minus. Again, our next step is going to be balancing the charges. This time we're working in basic conditions, so our charge balancer is going to be hydroxide. So let's count the charges on each side. This is 2 minus here, and then 3 times 2 minus here, so that's going to be 6 minus. So overall is 8 minus. And then on this side, we're going to have 3 2 minuses, so that's 6 minus. And to make these equal, we're going to need to add 2 minus to the right side. So this is going to be plus 2 OH minus. All right, so, and then we're going to need to balance the hydrogens, just like we did before with H+. We have 2 hydrogens on the right side, clearly, and that means we're going to need to add 1 water to the left side to balance the hydrogens out. And to check our answer, we're going to check the amount of oxygens on both sides. So on the left side, we have 1 oxygen from the water, 8 oxygens from the MnO4, and the 9 oxygens from the SO3 2 minus. On the right, we're going to have 4 oxygens from the MnO2 and 12 oxygens from the sulfates and 2 oxygens from the hydroxides. This side, when you add this together, that gives you 18. This side, when you add this together, that also gives you 18. The amount of oxygens are equal, we balanced it correctly. Therefore, we know that this is correct. And again, if you're really in a time crunch, you don't really need to check your answer by looking at the oxygens, but I recommend it when you do have the time to do so. All right, now we're going to add one more step, atom balancing. As you notice here, we have Mn going to Mn, and that looks just like we did before. However, we have this C2 going to CO2. And there's actually 2 carbons on this side and only 1 carbon on this side. All this means is we're going to need to write a coefficient of 2 in front of the CO2 before we get started to balance the atoms. So what I'm going to do is put a 2 right here. And now the carbons are balanced before we get started. So then we're just going to do the same process as before. So we already said that Mn in permanganate is going to be +7. And here we have 2 minus overall. Each of these oxygens contributes -2, so overall it's -8. And to give a 2 minus overall, that means together these 2 carbons need to be +6. Again, we're ignoring the H+. This is going to be +2, obviously. And then this carbon in CO2 is going to be a +4 oxidation state. However, we have 2 of them because we put a coefficient here. So we're going to actually need to write +8. Then we do the same exact steps as before. So 7 goes to +2. This is a change of -5. +6 goes to +8. This is a change of +2. What's the least common multiple of 2 and 5? Well, it's going to be 10. So that means we need to multiply the carbon reaction by 5 and the permanganate reaction by 2, so times 2. So we're going to have 2MnO4 minus plus 5C2O4 2 minus. We're going to ignore H plus. 2Mn2 plus. Are we putting 5 here? No. We actually need to put 10 because we need to multiply by this coefficient of 2 that we had initially. So it's going to be 10 CO2. And then everything's the same as before. We have hydrogens as our charge balancer, our protons. And there's 2 minus here, and then 10 minus here, so that's 12 minus overall. On this side, we have 4 plus. To balance that, we're going to need to add what's going to be 16 hydrogens to the left side, protons, so 16H plus. And then we're going to need to balance the hydrogens that we just added. So we added 16 hydrogens here, there's no more hydrogens on the left, and there's no hydrogens on the right. That means we need to add 8 H2O. And let's just very quickly check our answer. Oops, sorry, didn't mean to delete that. So here we have 8 oxygens here plus 20 here, so that's 28 oxygens. This side we have 20 oxygens from here and 8 oxygens here, 28 on both sides, so this is correct. All right, let's try one more example. So here we have chromium and nitrogen are going to be our reduced and oxidized atoms. So let's multiply the chromium by 2, so we balance the Cr2 here and the 2Cr here before the reaction. Nitrogen's already balanced because there's only one on each side. And then what we're going to need to do is the same exact thing as before. So here, overall is 2 minus. Each of these contributes minus 2. That means, so that's minus 14. To make overall 2 minus, that means these chromiums need to be plus 12. And then here, for HNO2, this is going to be minus 4 and then plus 1. That means this nitrogen needs to be plus 3 to make it overall neutral. Here, there's chromiums, each one is 3 plus, but there's 2 of them, so we need to write plus 6. And then here, the nitrogen is going to be plus 5, common nitrate ion. So let's figure out the amount of change for each of these reactions. So the chromium goes from plus 12 to plus 6, that's a change of minus 6. The nitrogen goes from plus 3 to plus 5, that's a change of plus 2. Least common multiple of 6 and 2 is 6, so we're going to need to multiply this reaction by 3. So we have Cr2O7, 2 minus, plus 3HNO2, and then goes to 2Cr3 plus, plus 3NO3 minus. Then we're working in acidic conditions, so that's going to be our charge balancer. This side we have 2 minus. This side we have 3 minus and 6 plus. So that's overall going to be 3 plus. To balance this out, we're going to need to add 5H plus to the left side. And then we need to balance the hydrogens on both sides. So on the left side, we have the 5 hydrogens here and 3 hydrogens here. That comes out to 8 hydrogens. On the right side, we have no hydrogens. So that means we're going to need to add 4 waters to balance the hydrogens out. Now let's check our answers by checking the amount of oxygens. So here we have 7 oxygens plus 3 times 2 plus 6. On the right side, we have 3 times 3, so 9 oxygens plus 4. So this gives us 13, and 7 plus 6 also gives us 13. These are equal, and that means this is our correct answer. All right, so that's probably enough for most cases, but there are 2 slightly different cases that I wanted to discuss, just so you don't get confused. There are disproportionation and comproportionation. So disproportionation and comproportionation, that's when, disproportionation is what we observe here. It's where one atom goes to 2 different oxidation states in a reaction. The way I like to approach these problems is by writing the species that goes under disproportionation twice. So we have HNO2 plus HNO2. All right, and then we're just going to write this all over again, NO plus HNO3. All right. Then we're just going to do the same exact thing as before. So this is going to be plus 3, like we just said. This is also going to be plus 3. This is going to be plus 2, and this is going to be plus 5. And we can consider them as if they were just independent reactions. So plus 3 to plus 2, this is a change of minus 1. Plus 3 to plus 5, this is a change of plus 2. Least common multiple of 1 and 2 is obviously 2. So that means we need to multiply this reaction by 2. So that gives us 2 HNO2 plus HNO2 goes to 2 NO and then plus HNO3. We can combine these together. So that's going to give us something like this. So it's going to give 3 HNO2. All right. Clearly the charges are already balanced on both sides, so we're just going to need to balance the hydrogens. So we can skip the charge balancing step here. On this side, we have 3 hydrogens. On this side, we have 1 hydrogen. That means the right side is deficient of hydrogens by 2, so we add 1 water. And to check our answer, let's look at the number of oxygens. On the left side, we have 6 oxygens. On the right side, we have 2 oxygens plus 3 oxygens plus 1 oxygen, which ends up equals 6. So this is actually our correct answer. And a very similar type of reaction is disproportionation. It's where an atom in 2 different oxidation states comes together to create a species where the atom is only in 1 oxidation state, in this case I2. So the way I like to approach these is a very similar way. What I'm going to do is imagine that this I minus is going to become an I radical, just a neutral I1, not I2. And this is also going to become an I radical. In a way, I'm splitting this into I and I, right? So the way this is going to look is like this. So IO3 minus plus I minus. Again, we're going to ignore H pluses and H2Os. Goes to I plus I, right? So this is not the I2, but I split it up. And then we're going to do the same thing as before. So IO3 minus, this I is going to be a plus 5 oxidation state. This one's going to be a minus 1. And clearly, these are both going to be 0. From here to here, the change is plus 1. And then from here to here, the change is minus 5. Least common multiple of 1 and 5 is going to be 5. So we multiply this reaction by 5. So we have IO3 minus plus 5I minus goes to 5I plus I. We can recombine these into 6I, which is the same thing as 3I2. So that's what I'm going to replace it with up here. 3I2. Then we're going to do just the same thing as before. We balance the charges. In this case, we're reacting in acidic conditions, so H plus is our charge balancer. On the left side, we have 6 minus. On the right side, we're neutral. That means we need to add 6 protons to the left side. And then we balance the hydrogens. So there's 6 hydrogens on the left, none on the right. That means we add 3 waters. To check if we're correct, we're going to look at the number of oxygens. On the left, we have the 3 from the IO3 minus, and that's it. On the right, we have the 3 from the water, and that's it. So they're equal, and we've balanced it correctly. So this is our correct answer. And that concludes our lesson on balancing redox equations. Please check out the practice problems in the description below that I've compiled from past USNCO exams. I'm not currently planning on making an answer key or guided solutions, but if that's something people are interested in, then I'll be happy to make a video. Just leave that in the comments below. Regardless, thank you for watching today, and I hope I taught you something new. Happy studying!